Sit back and look at the Andromeda Galaxy. It sits about 2.5 million light-years away from Earth. But if you were to dig into the original scientific papers published by the astrophysicists studying those stars, the term light-year is almost entirely absent. Instead, professional astronomers operate in a different language. They prefer units like the parsec, or strictly metric measurements like petameters and gigaseconds. This leaves us with a sharp scientific duality. Why does astrophysics maintain two entirely different rulers to measure the exact same universe? And why do the rest of us fiercely defend the light year, a unit that early 19th century astronomers didn't initially intend to use for stellar distances? How we choose to measure space reveals what we're trying to do with it, whether we're trying to mechanically solve the math of the cosmos or simply figure out our existential place within it. To understand the professional toolkit, we start locally. Within our solar system, distances are gauged in astronomical units, or AUs. 1 AU is the roughly 93 million-mile gap between the Earth and the Sun. Once you move beyond our solar system, professionals switch to the parsec, which equates to about 3.26 light-years. The word itself describes a physical technique, the parallax of 1 arcsecond. This is the geometric logic behind that name. If you observe a star, wait 6 months for the Earth to move to the exact opposite side of the Sun, and observe that same star again, you create a massive triangle in space. Because your viewing angle has changed, that relatively close star will appear to shift side to side against the much farther, static background stars. This visual shift is the parallax. If an astronomer measures that angle to be exactly 1 arcsecond, a tiny fraction of a degree, the geometric math will spit out the distance to that star as exactly 1 parsec. The parsec is an observational tool born out of strict necessity, allowing researchers to translate physical telescope movements directly into distances. But if the goal is scientific precision, why not standardize everything using the metric system? We could easily measure light travel in gigaseconds, that is, 1 billion seconds. 1 billion seconds mathematically translates to roughly 31.7 Earth years. If someone tells you a star is 4 light gigaseconds away, the human brain short-circuits. We have no biological framework to intuitively grasp what 1 billion seconds actually feels like. That is the problem the light year solves. Defined as the distance light travels in 1 Julian year, it covers a staggering 5.88 trillion miles. The year works as a baseline because it is a cycle built into our biology, our cultural history, and our physical experience of the Earth's orbit around the Sun. A unit of measurement is useless for communication if the public cannot visualize its physical scale. By tying distance to an intuitive span of time, the light year performs a unique trick. It functions simultaneously as a ruler for physical space and a clock for the passage of time. Because light has a strict physical speed limit, about 186,000 miles per second, it takes time for that illumination to cross the void. Looking across vast distances inherently means looking backward in time. Take Proxima Centauri, the nearest star to our own. It sits 4.25 light-years away. When you look at it in the night sky, you are physically observing the light it emitted over 4 years ago. As you scale that concept up, the delay becomes immense. You look past our local cluster, through the dense arms of the Milky Way, out into the intergalactic medium, peering deeper and deeper into history. This image captures the galaxy GNZ11, located 13.4 billion light-years away. The red smudge you see here is light that left its source just 400 million years after the Big Bang. Because of this universal time delay, every observatory and satellite we point at the dark is functioning as a literal time machine. The parsec is how humanity calculates the cold mechanics of space, but the light year is how we comprehend it, tethering the infinite void directly to our own human timeline.